a tiny capsule for astronauts. 25,000 miles per hour. What happens in the next 20 minutes will define human spaceflight forever. This is Artemis II, NASA's first crewed mission to the moon in over 50 years. And re-entry is everything. 50 years after Apollo, NASA is sending humans back to lunar orbit. But the return trip is more dangerous than ever before. For crew members are aboard Ariane, trained for years for this moment, trusting a heat shield with a known flaw. At 25,000 miles per hour, Orion hits the atmosphere 32 times faster than sound. That energy has to go somewhere fast. Mach 32 is not just a number. It is the point where air molecules stop moving and simply compress into superheated plasma. The capsule exterior reaches over 5,000 degrees Fahrenheit, hotter than molten lava, hot enough to vaporize most known materials instantly. Returning from the space station is completely different. Lunar re-entry carries 3 times more energy, creating a far more brutal atmospheric collision. The heat shield is the only barrier between the crew and certain death, a carefully engineered material designed to burn so they don't. AV coat is an ablative material. It deliberately chars and burns away, absorbing thermal energy before it ever reaches the capsule structure underneath. In November 2022, NASA launched Artemis I, an uncrewed test flight designed to prove Orion could survive the full lunar re-entry journey. Artemis I completed re-entry and splashed down safely. Mission declared a success, but close inspection revealed something deeply alarming on the heat shield. Engineers discovered unexpected cracking and material loss across the AVCoat heat shield, damage patterns that nobody had predicted. From any pre-flight simulation or model, outgassing trapped gases, violently escaping through the material during peak heating, caused chunks to break away, far earlier than any design model anticipated. The damage did not compromise Artemis I, but with crew aboard, the exact same failure could have been catastrophic and unsurvivable. NASA launched a full investigation, testing replacement materials, running simulations, and ultimately deciding whether to redesign the mission or redesign the shield itself, rather than replacing the heat shield entirely. NASA engineers redesigned the re-entry trajectory, adjusting the angle to reduce peak heating stress on the material. The skip re-entry technique allows Orion to bleed off speed across 2 atmospheric passes, spreading thermal load instead of absorbing it all at once. Re-entry begins at 400,000 feet above Earth, called entry interface or thin atmosphere. First begins pushing back against the Orion capsule's forward momentum. Before hitting the upper atmosphere, Ariane must rotate precisely, heat shield facing forward. Any misalignment means instant, catastrophic breakup of the entire vehicle. Compressed air in front of the capsule cannot move fast enough. Molecules ionize, and a glowing plasma sheath envelopes the entire vehicle completely. Plasma blocks all radio communication. Mission control loses contact completely. For several agonizing minutes, no one on Earth knows what is happening inside the inside. The crew experiences crushing G-forces pressing them into their seats, while fire surrounds every window, and they can do almost nothing at all. Crew members endure forces up to 8 times normal gravity, enough to make breathing difficult and cause temporary vision loss. Without proper physical conditioning, the outer AV coat layer glows white, chars and deliberately peels away each burning fragment, taking thousands of degrees of thermal energy safely with it. While the exterior burns at 5,000 degrees, the crew cabin stays near room temperature, separated by just inches of engineered thermal protection material. Peak heating lasts only 90 seconds, but in those 90 seconds, more thermal energy hits the shield than any other phase of the entire mission. At precisely the right moment, Ariane's lift generates enough force to skip back out, giving the heat shield critical time to cool slightly. The second entry arc is slower and more controlled. The skip has done its job, and the capsule now targets the Pacific Recovery Zone. Signal returns. Mission control erupts. The crew's voices crackle through static, confirming they are alive. and the vehicle systems are reading nominal. At 25,000 feet, drogue parachutes blast out. Small but powerful, their only job is to stabilize the tumbling capsule before the main chutes deploy. 3 massive main parachutes inflate to over 116 feet each, slowing Orion from 300 miles per hour down to just 20 miles per hour. Splashdown, Orion hits the Pacific Ocean and the crew is home. The most dangerous re-entry in modern spaceflight history, completed successfully. Recovery teams reach Orion within minutes. Divers secure the capsule, attach flotation collars, and begin the careful process of bringing the crew safely aboard. Each crew member exits the capsule and is immediately assessed by medical teams, their bodies having just survived one of the most extreme physical experiences possible. Post-mission analysis begins immediately. Sensor data from hundreds of embedded monitors will reveal exactly how the redesigned trajectory performed under real lunar re-entry conditions. The recovered heat shield goes under intense inspection. Every crack, every burn pattern, every material loss zone, mapped to validate the redesigned trajectory's effectiveness. Comparing the 2 heat shields tells the real story. Did the trajectory adjustment actually solve the cracking problem, or did it merely reduce it? Physics is the enemy. The moon is further away, meaning Ariane arrives with nearly double the kinetic energy of any space station. Return vehicle. Apollo capsules face the same lunar re-entry physics, but Orion is heavier and modern safety standards demand far greater certainty of crew survival. The entry angle must be precise, within a fraction of a degree. Too steep means burning up. Too shallow means bouncing off into permanent orbit. Orion's autonomous guidance computer makes thousands of corrections per second during re-entry, far more precise than anything human hands could manage. Under those conditions, mission control monitors every parameter, but cannot intervene during blackout. They have planned for every scenario, and now can only watch and wait helplessly. Crew training for re-entry spans years. Centrifuge exposure, emergency egress drills, pressure suit protocols. Every possible failure mode rehearsed hundreds of times over. The communication blackout lasts roughly 8 to 10 minutes, an eternity for mission controllers, during which the entire fate of the crew is unknown. 60 years of heat shield development, LED to AVCOAT, a material that proved itself in Apollo, but has never faced modern lunar return demands. Data from Artemis II directly shapes Artemis III, the first moon landing since 1972 where re-entry must work flawlessly. After astronauts walk on the lunar surface, future missions will stage through the Gateway Lunar Station, meaning Ariane may need to survive even longer transit times before facing the deadly re-entry gauntlet. Every lesson NASA learns from Artemis II re-entry flows directly into commercial spacecraft design. Orion is not just a capsule, it is a blueprint. The European Space Agency built Orion's service module. Their engineering is part of every maneuver that positions the capsule perfectly for re-entry success. Behind every decision is mathematics. Thousands of equations computed over years of simulation, all converging on one trajectory that keeps 4 humans alive. NASA has mitigated known risks, but space exploration always carries unknown risks, and re-entry remains the phase where engineering meets pure uncertainty head-on. The parachute system alone required over 600 individual tests, each one validating that 11,000 pounds of capsule can be safely slowed by nylon. Even at 20 miles per hour, hitting the ocean surface transmits enormous force through the capsule structure. Survival seats absorb that energy before it reaches crew. History reminds NASA what failure costs. 17 astronauts lost on Challenger in Colombia. Every Artemis engineer carries that weight into every single design decision. Solving lunar re-entry is not just about the moon. It is the essential step toward Mars, where astronauts will face even greater return challenges. The world is watching. Artemis II is not just a NASA mission. It is humanity's reminder that the most dangerous journeys are still worth taking. when those parachutes open and Orion hits the water safely. Every engineer who spent years solving this problem will finally be able to breathe. 25,000 miles per hour, 5,000 degrees. 8 GS, 10 minutes of silence. 3 parachutes, and 4 astronauts who made history returning from the moon. Thanks for watching. For more amazing space facts, subscribe to Planet Facts. And don't forget to hit the bell icon to stay updated.